buttons to... Okay, thank you. So I'm going to make great use of what Hugo has just presented for a different group of sources. I'm going to talk about the sources from the XM Newton optical monitor. So these are ultraviolet and optical sources. And on reviewing my presentation this morning, having submitted it on Saturday, I obviously worked very late at night to get this finished because I noticed I've spelt Keir's name wrong on the first slide. And I've also written Claxboy as Claxbol, I think, in the various slides. So I've, at the risk of alienating the most important people who've contributed to my talk, there we go. Anyway, first of all, I better say this is on behalf of colleagues where I am at MSSL, also Santander, Leicester, Athens, Potsdam, Strasbourg, and the cast of people who contributed, particularly at the bottom. I think it's fair to say the person who's done the most work on everything I'm going to report is Paul Cowan, who's the first person listed there. Okay, so to introduce this, XM Newton's been flying now for 25 years, almost. So that's 25 years of the XMM SSC and others working to characterize the X-ray source population, but characterizing the ultraviolet and optical source population that's being picked up in almost every XMM observation with the XMM-OM hasn't had very much effort put into it at all. And in a systematic sense, it hasn't had any effort really put into it until now. But the catalog's got more than 6 million unique sources, and it's still going up like everything else. Now, optical data, arguably, it's to a penny. There's truckloads of it out there from ground-based and space-based surveys, but UV data is quite valuable because it's really rather sparse and rare. And in the case of the XMM optical monitor, it's simultaneous with the X-ray data. So this means, and it's true for the optical data as well. So that gives it a particular value if you're interested in X-ray optical sources. So these data are really missing out on a classification scheme. So that was the motivator for this part of the XMM to Athena project. Okay, so our objectives here are to classify the sources in the XMM Newton Serendipitous UV Source Survey, which is acronized to be the XMM SUS, but it basically means the catalog of all things detected in the XMM optical monitor, intergalactic and extragalactic source types. Now, in previous times, as I'll show you in a slide or two, we know we can classify some of these sources where we've got rather dense data coverage and we can make diagnostics. But the real thing we wanted to achieve was to get broad coverage. So wherever your OM source was and whatever observation mode it had been taken in, however much data you got, we could make an attempt at classifying what it was. And then the plan is that once we've classified the sources into galactic and extragalactic types, we'll be adding photometric redshifts for all the extragalactic sources, because of course that will make them much more useful. Okay, so before XMM to Athena, understanding of the OM source population probably is not much more than you see on this slide here from the 2012 paper that accompanied the first release of the XMM SUS. And you can see the optical and the ultraviolet. Ooh, where's my pointer? This button. Ultraviolet colors, right? So these are the ultraviolet filters on board the XMM optical monitor at 2000, 2300, and 2800 angstroms is UVW2, UVM2, and UVW1. And then you've got your optical colors. Okay, pretty familiar, old school astronomy UVB over there. And underneath these two plots of data, you see model colors for stars in this panel and galaxies in this panel. And basically, you get a lot of diagnostic power in the ultraviolet. And most of the stars lie on this arc here, right, which corresponds to this arc here. And hot stars live down here, and cool stars live right up here. And basically, all the extragalactic sources that OM is picking up in the ultraviolet. So, of course, this is in a sense a biased sample of galaxies and quasars. This is all the ultraviolet bright ones inherently you see in this big blob down here. Morphology helps for the brighter sources to split them up, but doesn't help very much for the fainter sources in XMM OM data itself. In essence, when you get really faint, everything looks like a point source to XMM OM. Though the spatial resolution is not bad, it's about 2 arcseconds in the UV. It's just a signature noise thing. If you just have the optical colors, you don't have very much diagnostic information here. But the real problem is plenty of, I mean, people choose whatever filters they like for the XMM optical monitor. So there's a huge diversity in what we've actually got for any one source. You might only have one measurement in the V band, and that's it. And there's no way you can do a diagnostic based on one measurement of photometry. So that's really the challenge that we've got, the diversity of coverage in the different bands and so forth. So the first thing we did fairly naturally is to connect up our XMM optical monitor sources to large area ground-based and space-based catalogs to augment our OM catalog with ancillary data that's going to be useful in classifying those sources. So this means WISE, Gaia, Sloan, Pan-STARRS, and so on, obviously, and we were prioritizing things with a large sky coverage because we're aiming to classify a large fraction of the sources. Now, we have some things that make life easier for us and things that make life harder for us compared to what we've just heard from Hugo on X-ray sources. On the good side, OM positions are sub-arcsecond. So we don't do very complicated source association. It's a simple sky matching TopCat nearest source within a couple of arcseconds. And it works most of the time. Doesn't work perfectly, but it works most of the time. And we're going to gloss over any problems on that. Of course, there'll be some funny sources and genuinely confused sources and so forth. On the harder side, we've got 6 million sources, whereas in 4XMM, there's less than 1 million. So we've just got a volume issue, really. And then we had to decide how to classify these things. And we've ended up going with Klaxboy, which has been fabulously described by Hugo just a minute ago. And I think we thought about this quite hard, possibly not as hard as some people have. But I don't think so the big problem is the inhomogeneity, right? Even the large area surveys, Sloan covers one bit of the sky, Pan-STARRS covers another bit of the sky, UKIDS gives you infrared data on another bit of the sky, Vista gives you slightly different infrared data on another bit of the sky, WISE gives you the whole sky, but lots of things aren't detected. Gaia covers the whole sky, but lots of things aren't detected. So there's a lot of missing data. And that was really the problem we had. Now, we know we can do extremely well in classifying things with more complicated algorithms, even classical, like old school stuff. And the people at Santander showed this. You could get a very, very good classification using principal component analysis when you've got uniform and dense coverage of data. But for what we wanted to do to get for those 6 million rather than the most interesting 300,000 sources, it just isn't going to work for us because of all these data gaps and so forth. And the inhomogeneity was important. And the Klaxboy actually really deals with that quite well. It's got a simplicity to it, which is really helpful. And then when we did try various ways of classifying things, we've learned, probably like anybody else who's had a go at this whole thing, that it's really easy to make a total and utter mess of this, but convince yourself that you've done a brilliant job. And this is quite scary truth. And the great thing about Klaxboy is we could understand what was happening. So we could work out when we were stuffing it up completely. And that's really powerful. Now, the bottom point here is obvious. Everybody will tell you this. In fact, I've already heard Mara saying this earlier on in this meeting, rubbish in, rubbish out. But it doesn't look like rubbish when you're putting it in until you realize and think it through quite what you're doing. And that's really a key thing. Okay, so the key thing with Klaxboy is your training set. So we needed a set of galactic stars, galaxies, and quasars. And we wanted to split our extragalactic sources into these two basic categories. A major point was our colleagues in Athens said they wanted to know when they were doing photometric redshifts whether they were looking at a point like quasar or an extended galaxy, because this tells them which version of the photometry used from the various catalogs and also what SED templates to be putting in. So that's the essential discrimination we need to do for the next step. And obviously, stars we want to split out completely from our extragalactic sample. But we haven't subclassified stuff within this classification process beyond that at this stage. And then we took some care, we didn't initially, but after we'd figured out what we were doing wrong, we took some care to make sure that our galaxy sample didn't actually contain a load of quasars or AGN in galaxies, because then it gets very complicated when your training samples actually overlap in parameter space because they're genuinely the same things. So that's a horror story. So we took care to separate them out. Okay, and then just to show where the training sets live in color space compared to that UV diagram I showed at the beginning, if you take those training sets and you pick out the ones that do have UV data in the XMEMO, and this was something that was very reassuring, right? So we thought from theoretical grounds, all the stuff in this arc here should be stars, and the stars we've got here. Okay, and I should say that the stars are selected from Gaia through basically significance 10 or greater parallax. So we simply know they're stars because they're in the galaxy, and we know from geometric means how far away they are. There's no color information or anything like that. So that's good, but it's also bad, as we'll see later. But anyway, they cover this range quite well. Quasars, galaxies, and they basically do overlap largely in this bit of parameter space here. So reassurance, okay, at least our training samples look like what we're expecting them to look like in XMMOM parameters. And then we go for the auto classification process in ClaxBoy. And we've got 12 parameters, and they're basically colors, spatial extent, and some sort of hybrid of those. I'll talk about each of these types of things in the next few slides. Now, in the end, we're not going to use, not using at the moment at least, location, flux or magnitude, as in apparent brightness on the sky, parallax, or proper motion. And I'll tell you why we're not using those as we go through these slides. So it's basically all based on colors, extents, and some sort of hybrid. And in all the plots, so you don't have to take very much from this. This is the kind of output that you get from ClaxBoy. But in all the plots, I'm going to show quasars are in orange, galaxies are in green, and stars are in blue. And hopefully, if you're colorblind, I've got those labels written close to the curves in the forthcoming plots, so you'll be able to identify which curves which as well. Okay, so the first criterion is color. Right? Everybody knows colors are going to be used to classify sources. This one's been used for more than 100 years to work out what things are on the sky. And of course, UV excess or U minus B has been used since the 1960s as a way of selecting quasars, for example. And that one's something we show here, and we've got the OM colors for those sources which have got both those color bands from the optical monitor. Okay, you see, and a typical characteristic of the OM sources going through ClaxBoy is you can isolate one group of sources from the other two, but you won't be able to isolate all three of them. It's very rare in any of these diagnostics to split them into three distinct bumps. But it's okay, because as long as you've got multiple diagnostics that discriminate different ones from the other two, when you put all the probabilities together, you should be able to split the population into its component parts, and that's the idea. Okay, we've actually got quite a few colors in here, and one of the reasons and issues for that, okay, thanks, is that there's just such a lot of different colors because of the different data coverage across the sky. Okay, the next thing is extent, how big a source is on the sky. Now, everybody uses this Sloan uses this, they make their own measurements of this. The problem for us is it's so inhomogeneous across the sky. If you take your data from Pan-STARRS, if you take it from Sloan, if you've got your measurements from UKIDS or something in the south, that all provide different or no information on this. So we found that a really good discriminator is the difference, the Gaia G-band and the ground-based G-band measurements, because Gaia is basically measuring things as a compact point source at very high spatial resolution, whereas ground-based we have seeing, so nothing's all that small. So if it's basically stars, all the flux gets picked up by Gaia. Galaxies, a lot of it gets missed. And you see in this ground-based, Gaia-based minus ground-based, the galaxies get pushed off over here. That's really quite reliable. We've got some composite color and extent ones. So this one does really work quite well. Stars, quasars, and galaxies all split apart quite nicely if you take Gaia G and minus Y's W1. If you take ground-based G instead of Gaia G, the galaxies and the quasars are all on top of each other. But once you add this extent thing in, it pushes them apart. That's really quite handy. So in this one, we can distinguish all three. And then how well does it work? So this is a confusion matrix. Okay, so this is like real things. What do they appear to be? Okay, so total number is the number of real quasars. This is the number of things that, sorry, real stars. This is the number of things that appear to be stars and so forth. So this is the truth. Obviously, everything in this category is good. But where does it go wrong? Okay, so stars do quite well. But the biggest problem is quasars leaking into the galaxy category or galaxies leaking into the quasar category. And so our recall and precision are high 90s for stars, and they're not too bad for galaxies, but for quasars, they're actually not as high as we would like. That's based on the training set. I agree with Sean, we should check that they're true on some independent data. So Paul has correlated with the Veron et al. 2010 quasar catalog. And effectively, it confirms our results as we've got them. The things which appear to be quasars in our classifications come out, turn out, okay, so we do a good job with the external data. Simple as that. In fact, we do slightly better with our external training set. Where are we going wrong? What are the worst problem sources? Those sources which are leaking between quasars and galaxies. The issue is actually really very simple. They're faint in the optical. They're too faint for Gaia. So you can see the Gaia completeness limits here. It actually cuts off somewhere at 21 point something. So basically, these are all quasars which are too faint for us to be able to tell whether they're point-like using Gaia. So that criterion fails, and that was one of the key things that we were using, okay, to separate galaxies and quasars. Okay, I don't have very many minutes left, so I'm going to be a bit quick on this one. You've got to be really careful how you mix your training sets and interpret what you're getting out. If you use parallax to select stars, so they've all got lots of parallax, and none of your quasars and galaxies have got parallax. If you try and use that as a criterion in Claxbol, everything with low parallax will be classified as a quasar and a galaxy. So the fact that we'd selected it in this way and have no low parallax stars means we can't use that as a parameter. And similarly, we haven't got the location, because the location of the Sloan Digital Sky Server, where we've got our quasar and galaxy training sets, is imprinted on the galactic latitude distribution. So effectively, there's nothing at the South Galactic cap in terms of extragalactic sources. So if you put galactic latitude into Claxbol with these training sets, it will tell you everything at the South Galactic cap is a star, which is obviously completely rubbish. It's an awful shame, because they'd be quite useful classifiers. I'll be very quick on this. Upper limits are actually quite useful and mean something, but there's no real easy way to put them into Claxboy unless I've just missed everything, thanks Hector S. But you can kind of shoehorn them in by sources which you know they are fainter, redder than this, let's say, in the Gaia minus ground-based G magnitudes. You can put them in with their Gaia G-based upper limits, and then it'll end up classifying them in the right way. So upper limits turn out to be really quite useful, though it feels a bit like I'm doing an old school classification scheme when I insert them in this way. Okay, here's what we get from the XMEM-SUS: 4.5 million stars, 200,000 quasars, 1 million galaxies. Most of the leakage is between quasars and galaxies. The stars are quite clean. So the galactic extragalactic split is quite clean. So you can start to do science. Here's a color magnitude diagram where you can split white dwarfs and red clump stars, and you can use those to investigate the ultraviolet properties of those. for example, luminosity functions of white dwarfs, or look at the galactic extinction curve variation using red clump stars. I'm going to speed through these science applications, so you can ask me about those if you like in the question time, but you can do a good job of selecting X-ray weak quasars. It may be useful in other contexts because for example, once we've classified quasars, even if it's not totally reliable, we could use that as the aspect correction sample to go into fix the attitude for XMM epic observations where that's failed for one reason or another in the current process, because the quasars are bona fide very high likelihood X-ray sources, a bit like Mara was describing is done for E Rosita. So in principle, there might be some benefits for XMM as a whole. And there's my conclusion. We've used ClaxBoy to classify the sources in the SUS catalog. 4.5 million stars, 1 million galaxies, and 200,000 quasars. It does a good job discriminating galactic and extragalactic sources, but there is some leakage between the extragalactic source types. And, well, classifications for the first run of this are available, and you can have a look yourselves. Thank you very much.
Thank you, Matt. So, is there any question? Please. What can I do?
Hi, thanks for the talk. Did you think to consider extinction for improving your classification? Because I know that extinction will affect stars that have less extinction, but for quasars, it actually help in grouping them.
Yeah, I thought about this, but so the situation is so different from what you're doing. And it was interesting to listen to what you were saying, because most of our sources are stars, and quasars are a tiny minority.
Yeah, so it can be a risk.
We can't blanket correct everything for extinction.
Okay.
Because most of our sources are, and even when you get down to the galactic plane, lots of our sources are quite nearby to not be to be detectable in XMMOM, let's say.
Okay, then
Yeah.
micro. The other problem is that Gaia detected the point sources in the nearby ciphers, that they don't detect the cipher itself. So you will have a type 1 broad line in Gaia, but it is in reality a nearby galaxy. So how do you classify these objects?
That's a good question. But so Gaia, well, okay, it depends on the contrast between AGN and host galaxy, right? If the AGN's making most of the flux, our extent discriminator is going to make it look point-like, so it'll probably look like a quasar. If the AGN's not contributing very much to the flux, the Gaia measurement will be quite a small fraction of the galaxy, and it'll look like it's extended when you contrast it with the ground-based measurement that includes all the flux from the galaxy around it. So in that sense, it will look like a galaxy, and we'll class it as a galaxy. So the reality is there's some sort of threshold there. It's a little bit of a problem in a way. You want to class things into either galaxies or quasars, and we know there's a horrible overlap region in between. So exactly where the dividing line lands in our sample could do with some examination, but of course it's also probabilistic, so it's a little blurry, let's say.
Okay, so I go with one.
Yeah, quick question. Stephen Chen. So when you compare the Gaia G-band versus the ground-based G-band, as far as I know, the Gaia G-band is very wide. Is the ground-based G-bands also like comparably that way, or is it?
No, so you're quite right. They're not the same. And so the reality is there's a color term. So this adds scatter, basically. And so even for stars, you see quite a variation in Gaia versus ground-based. If I flick back to it, where did we have this? So in principle, if you didn't have, right, so if Gaia had the same G-band as the ground, then this really ought to be a very narrow distribution, whereas this width here really reflects the photometric errors and the width of the G-band, so color terms that come in there. When it comes down to it, those color terms are still small compared to the difference when you use this ground-based versus Gaia G-band in terms of extent.
Yeah, that's really interesting. And is the ground-based G-band, would that normally be a capital G or lowercase G?
No, it should be a lowercase g,
Thank you.
sorry. Yeah, I've been a bit sloppy on capitals, lowercase on all of this.
Okay, so we don't have time for more questions, maybe in the break time. So thank you very much.